Good evening, sir.
Shall we start? So, welcome to the second session of the basic electromagnetism, PHU 3301, the day school session. Now we have already completed the unit 1. From today onwards, we are going to conduct the unit 2. Right, please place your just a registration number and the CRC or regional center, CRC, JRC, whatever it is. I don't know why this student number is actually very less. Maybe some of them actually that is working. Then most actually, I think there are nearly 100 students are actually registered here. Right? Everybody has participated in the exam, no? Anybody? Okay, good. Right. So actually that the Zoom session means we must have some interaction between you and me, right? So therefore, whatever the question we're asking about, please reply. Okay. Right. This totally that based on this the unit 2, that is magnetism part, right? Magnetism part. Right, there we are discussing about, if I give you this brief about this the unit 2 magnetism part, that means magnetic field. First, actually, we'll start with the magnetic field, right? Then the electromagnetism. Electromagnetism means that is the magnetic field due to current carrying conductors, right? When the current is actually passing through there, there's a magnetic field generated. We are developing some expressions and some applications there, right? Then the force due to magnetic field, current carrying conductor, then there's a force according to Fleming's left-hand rule, right? Then the Fleming's right-hand rule due to the Fleming's right-hand rule, when there is a force and the magnetic field is actually available, then there is a current actually generation there, that is called induction. Then some application of this right-hand rule. Then after that, the charge in the magnetic field, right? Moving charge in the magnetic field, right? The force on the charge in a magnetic field, right? There's a force when the charge is actually moving in the magnetic field. So there actually we have some expressions, right? That then the properties of the magnetic field, right? Diamagnetism, paramagnetism, and ferromagnetism, those things, right? Then the related theories behind this, why this the magnetic field actually generated. then some amperes law, then hysteresis loop, then actually that is related to the experiment. You may have already done this, the hysteresis experiment. Then the application of left-hand rule and right-hand rule, the moving coil galvanometer and the motor, right? Ballistic galvanometer, application of the working principle of the ballistic galvanometer, right? Then the induction, electromagnetic induction, it is called application of the right-hand rule. Then induction, then the current, the AC current actually passing through the inductors. I mean the three components: the inductor, capacitor, then the resistor, right? Impedance, then the transformers, the working principle of the transformers, then the efficiency of the transformer, transient phenomena, that means LCR circuit, LR circuits, series, parallel. Transient circuit means if we have LCR circuit that is connected to the DC supply, right? And remember that one, this is actually very, very important one. When we have the three components, as I mentioned about the inductor, resistor, and the capacitor. These three components, when we are conducting, when we are connecting these three components, maybe in series, maybe in parallel, to the DC supply, to the DC supply, right? Then what are the equations related to that one? Then what is happening there? How the charge is actually stored in there? Then the current is actually passing through the circuit, right? The variation of the current and the time, right? That actually we have to discuss. And there are so many equations actually. That is not, that is not, I mean, those equations are very, very simple, but don't make it actually complicated. I will tell you that the simplest way to learn those things, right? That is actually related to the connecting the DC voltage. Next one, actually, when you are connecting these three components to the AC voltage, right? So the AC voltage, that is called alternating circuits. It is also LCR connecting to the alternating circuits. That means series, parallel, and the yeah, that is the last one, right? Impedance. So those things actually we have to learn, right? So most probably that there are more questions coming from the transitions and the LCR transition and the AC voltage, right? So so remember those actually, that is not so difficult. We will make it easy to understand. Right. The first part is actually that is the basic things, but the problem is actually whatever you have learned at the A level, whatever you have learned at the A level, those are actually just a equations type. But here actually we are using some the mathematical expressions, right? Here we are using some mathematical expressions, some integrations, the differentiations, right? Or vector notations. By this is the way we are representing these expressions, right? So therefore, maybe it is not familiar to you, but you may have already done this the mathematics part. Those who are actually following in the bio stream, they have followed the bio stream. I mean the mathematics one. Then they will you can learn. You may have already learned those mathematics parts. Then when you are conducting this that course, mathematics for biology and biology student. Then the math stream actually that they can easily understand this calculation one, that integration and the vector notations, right? Now that is the difference between that here and the A level, right? So now we are representing these equations in some mathematical notations, right? Some mathematical notation expression. So we are going to derive these ones by using those. So but the mathematical part is actually we are not considering, but the way of representing that is actually very, very important. All right. Now shall we move on to the section? Right. The magnetic fields and line of induction. Right. And you know that if we have a magnetic field, that means we can call it actually field lines. Field lines as the flux, magnetic flux. Right. So the flux actually, normally we will define as a flux density. Flux density, that means flux density means the amount of flux passing through the unit area. Amount of flux passing through the unit area, that is equal to the magnetic field strength, or right, magnetic field strength, that is called the B, or the magnetic field, right? So the magnetic field B is equal to flux density, right? Flux density means the flux, magnetic flux passing through the unit area, that is equal to the strength of the magnetic field, right? So that is the way we are writing about. Now we will write the same thing in a different way. Right, this is the way. The direction of B, right? Remember that one, the magnetic field, that is a vector. That is a vector. It has a direction and the magnitude. So the direction of the B at a point in a magnetic field is the direction of the tangent, right? Suppose if there's any field line, right? Maybe the curved one, right? Or the straight line. So that when you are drawing the tangent to that point, right? Yeah, when you are drawing the tangent to the field line, that is equal to that direction. Actually, that tangential direction is called that is the direction of the magnetic field, right? That will represent the direction of the magnetic field, right? That is called the direction of B at a point in a magnetic field is the direction of the tangent to the line of induction at the point, right? So total number of lines of induction crossing a given surface represent the magnetic flux, right? You can see that there are some the selected area there, right? So selected area, then field line is actually passing through there. So then the field magnetic flux actually represented by the B dot ds, the B dot ds, right? Integration of the B dot ds, right? So actually B dot ds that will actually represent by what? Anybody can explain? The magnetic flux is how we are going to represent that one. Magnetic flux is it will actually represent as a B dot ds. How do you say that? Flux means, is it
B means flux over area.
yeah, that is correct. And that is actually flux. No,
yeah.
flux over area is that is equal to the B. I'm asking about flux. The definition of flux actually, that flux means is it vector or scalar? Yes. You know that the dot product is actually representing what?
Scale.
Sorry?
Scalar, no? Sir?
Scalar. So that means it is a scalar, no?
Yeah.
Yeah, that is a scalar. B dot ds is actually, you know that there's a dot product and the cross product, right? Cross product is actually that is representing the cross product is actually representing a vector, right? So that means the whatever we are representing, that is also a vector. But here we have the dot product, B dot ds. B is a vector. B is a vector, right? B is a vector and ds is also vector. But the product of that one is actually representing the scalar. That is called the flux, number of field lines passing through that the selected area, right? Number of flux passing through that the selected area, right? We represent as a B dot ds. Right. Now magnetic field of a moving charge. This is the way we are representing the magnetic field due to moving charge, right? That is already in your book. That is figure 9.1. I will show you this. Right. Now you can see the figure. Can you see the figure?
Yes, sir.
There's some bright spot in my whiteboard. Is it disturbing you?
I can read it, sir. I don't know
Okay,
about.
good. Then actually that in the figure 9.1, we are in the same thing, right? But remember this, see, the charge is actually moving in this direction. Charge is moving in this direction, right? Remember this one, the story behind this. The charge is actually moving this, right? Now, because of this charge, so we want to find the magnetic field somewhere here, P point. You want to find the magnetic field somewhere here, that P point. The charge is actually moving in this direction with the v velocity, right? With the v velocity, right? In this case, the magnetic field. So therefore, we want to find the magnetic field at this P point. So there actually we have to draw the charge is actually moving from this direction. From this point onwards, we should draw the line between this P and the charge where we have started the moving actually, right? Still it is moving. Now at this point, we want to check the when it is actually that is here, the charge is actually here. We want to find the magnetic field here, right? When the charge is actually moving, still it is moving with the v velocity at that particular point, right? So therefore, we want to draw the line between this point, the charge at the temperate stop, and this point, the P line joining between that, right? So there we have the distance that is equal to the R, right? That is R. So change it, right? Then the V. So there's an angle between this the direction the charge is moving and the line between this the line we have drawn from the P to the charge. That is the angle that is called theta, right? Now the magnetic field actually you can see the magnetic field is actually that perpendicular. Magnetic field you can see that one there is a perpendicular line. Magnetic field is actually that is in this direction, the tangential direction. This is actually the field line, right? So if I draw it somewhere there, that is in this way. So therefore, magnetic field is actually the perpendicular to the the R or QP line, right? QP line. Our magnetic field is actually like looks like this one with a circle or something like that, right? So in that case, if you want to write down the magnetic field here, magnetic field is here. We know that magnetic field is also a vector. Magnetic field is also a vector. So therefore, there should be a representation of the vector ones, right? So how we are going to represent that? How we are going to represent the magnetic field due to this charge, moving charge, the B is equal to mu naught divided by 4/5 QV. QV is a, but V is a vector. The cross product of R divided by R square, right? So this is the way we are representing the magnetic field at R distance. That is, we have selected like this point, right? And the distance from this Q to the P is that is R, and the vector in that direction. Vector, the distance between the QP is equal to R, but vector in that direction is equal to R dash, right? R, vector in that direction is R, right? So R, and we know the velocity is actually velocity is actually that is in this direction. So what we have to take? We have to take the cross product of that. We have to take the cross product, right? Cross product of the vector R and the V, right? Vector R and the V. But here we have taken the cross product. So the cross product means that it will indicate the final outcome is the vector. But that is also a vector. The magnetic field is also a vector. So therefore, the final outcome or the magnetic field is actually representing and this expression, right? Finally, that magnetic field is actually that is representing in this expression, right? This is the description of the magnetic field of a moving charge. This is the one actually we have here, this equation, right? Vector B can be written as mu naught 45 q v. V is called the velocity vector, and r, the direction of the OP. In that direction, the vector, then divide by the distance r square, distance between the q and the p. Right? So remember this, and by using this, sometimes we are deriving some expressions, right? So basic one is actually this. Right. Now the first law says the Biot-Savart law. It is, but this Biot-Savart law and whatever I have discussed earlier, it is a different one, right? This will also represent the magnetic field that is due to a moving charge. The Biot-Savart law says the current carrying conductor, due to the current carrying conductor, the magnetic field around that, right? So this is actually represent the Biot-Savart law. So the Biot-Savart law, you can see that one, the ds. So we have a current carrying conductor, right? Current carrying conductor there. Then there actually we are selecting the small element, right? Length of small element as ds, right? Then we want to find the magnetic field at P. Magnetic field at P. Magnetic field at P here. We want to find the magnetic field here. Then you can see that, and this is our current carrying conductor. This is our current carrying conductor. Then, but there actually we are selecting the small element ds, the small element, right? So the Biot-Savart law. No, in the earlier case, when we are doing the A level, the Biot-Savart law says the when we are current carrying conductor, the magnetic field that is proportional to the I delta L, that is current segment, and the distance and the angle between that. So magnetic field. Now we are going to write we are going to represent this one as a vector representation, right? Earlier it is a normal representation by using these symbols. Now in this case, the here we are taking that the ds small element along the current carrying conductor, right? There actually we are taking that IDS, the small segment, right? Then the B, the magnetic field at B, right? We can call it as a delta B, right? The delta B is equal to mu naught 4 pi divide by 4 pi IDS cross product as R. R is the vector. The line joining between the point and the P point, the selected point on the current carrying conductor, and the P point, the vector in that direction, divide by the R square. R square is called the distance between the the selected point on the current carrying conductor and the P, the R discussed. But R dash is called the vector in that direction, right? It is called, that is R dash is called the unit vector in that direction, right? Unit vector. See the where the dB is the, and dB is also represented in the vector because it will represent the magnetic field. Magnetic field, actually we know that is also a vector, but remember that one. So far we haven't discussed about the direction. So still we are talking about this, the magnitude value. This is the way we are represented, getting the magnetic value. Right. Anybody? So therefore, suppose that if we want to get some other the combinations, right? So some applications. So therefore, this is due to a small segment or small element, right? Now, if you want to consider about the surface or the whole line or whole area or whole our object, then we have to integrate from the one point to the other, Any clarification about this? Anybody wants more details about this? Yes? Anybody? Anyone? Okay. This is the way. Now you can see that the way of representing the direction, because we know that magnetic field is a vector. Now, so far actually we have discussed about this magnitude value. Now the direction. There are two. I mean, there are two methods actually. One is called the screw law, the right-hand screw law, right? It is a right-hand screw law. So when we want to tighten the screw, right? So we should when we are rotating in this is called the clockwise direction. When you are rotating the clockwise direction, the screw the screw is actually moving down. The screw is actually moving down. So therefore, that will actually whatever the direction the screw tip of the screw is actually moving, that is called the direction of the current. So the rotational direction, that will represent the magnitude, direction of the magnitude, right? Direction of the magnitude. This is called right-handed screw law, right? Maxwell's right-hand screw. There is another method, the same thing actually, that there also we are using the right hand, but you can see that it is called grip rule, right? So suppose if we have a right hand, then when we are gripping that, suppose if we want to hold this one, then the thumb actually representing the that is the thumb is actually it should represent the direction of the current. Suppose you can see that there's a current carrying conductor, the current is actually passing through the top top of that one. So therefore, that when you are using that right hand grip rule, right? So we have to hold this the current carrying conductor, that our thumb should be in the direction of the current. Then the rest of the fingers actually represent the direction of the magnetic field, right? Direction of the magnetic field. That way also we are finding the direction of the magnetic field. So therefore, that is the two ways. There should be two things actually. First, we have to identify the one is actually the direction of the current, the other one actually direction of the magnetic field, right? This is actually totally due to the current carrying conductor. So therefore, the current is also there. Then due to the current, there's a magnetic field. So therefore, we should know about that the direction of the magnetic field also due to this current. Right. Now we can see that application of the Biot-Savart law. Application of the Biot-Savart law. Right. Application of the Biot-Savart law. You can see if we are having the magnetic field due to a long straight wire, right? Not the shortest one. That is called the long straight wire, right? You may have already learned that due to this, the long straight wire, the magnetic field from the perpendicular distance from the current carrying conductor, say R, then the magnetic field is equal to mu naught I, because the current actually passing through current conductor, current in the conductor, that is equal to I. So therefore, we are finding that R distance from the current carrying conductor, perpendicular direction from the current carrying conductor. So the magnetic field due to that point is equal to mu naught I divided by 2 phi R, right? But in your A-level section, right, in your study in there, you don't need to prove this one. But now you should know how to prove this, right? You know how to prove this. So then first thing, actually, we should identify this, how to write that basic expression. We know that here we are using this Biot-Savart law, application of the Biot-Savart law, right? Then there's some mathematical parts. So therefore that you can learn that mathematical parts later on, right? So only thing, actually, physics you should know. Then I will right. You can see can you see the whiteboard?
Yes, sir.
Okay, good. Right? This is infinitely long current carrying conduct. Infinitely long. So therefore, here also there, this is never ending. Right? So we want to know about this magnetic field from this point, the perpendicular this point, R from here, the P point. Right? So therefore, we are how we are going to write it. We'll take that the small ds segment here, ds segment. Due to this ds segment, we will ds segment, and perpendicular point to the ds is equal to s, and this is r. From that point to the distance from the selected point from the ds element to the p is equal to r vector. Right, now we can write down, due to this small segment ds, the magnetic field due to ds small segment, due to this small segment ds, the magnetic field at this P point, we can write it down, dB is equal to mu naught divided by 4 phi by using the Biot-Savart law. I, because the current actually passing through the conductor, that is equal to I. IDS cross R divided by R square. R square, not the cube, right? It should be R square, right? It should be R square. Now, I will take the, this is a vector representation. ds is also a vector and R is also a vector. Oh. Igual. Right. Hari. Right. Oh my God. Right. Now, this is the vector representation that, as I have mentioned about this Bhavishavat law, by using the Bhavishavat law, we can write down due to this small segment. Due to this small segment, the magnetic field at B, right, is equal to the dB, right? So therefore, that is equal to this one, right? Now we can write down. We can take the cross product of this. Anybody can say that what is the cross product of this? Yes. Anybody? How we are going to write down the cross product? Now dB is also a vector now. dB is also a vector. And this is the way we are, by using this vector representation of the Biot-Savart. Vector representation of the Biot-Savart law. Right? Anybody can say? This is I have written the application. I have applied the Biot-Savart law to the ds segment, right? ds segment. Right? Now, when you are dB mu naught divided by 4 pi, right? I, this is the cross product, right? That is a cross product. And I ds and R sine theta. It is a sine theta, right? So we will take this you know that when we are taking that cross product, there should be a perpendicular. There should be a perpendicular vector, right? That will actually, we can take it as ijk, right? K. Then when you are taking the modulus of that one, it will become 1, right? So modulus of ds, modulus of r, modulus of this one, then the angle between this the r and the ds, right? That is sine theta, right? So therefore, that will equal to mu naught divided by r square. So mu naught divided by 4 pi I. When you are taking the modulus of this one, that is equal to ds. When you are taking the modulus of the unit vector, that is equal to 1. So the sine theta divided by r square, right? Divided by r. So IDS sine theta divided by r square. Right? Now, anybody? Any clarification? No, that is okay. Can you see the whiteboard?
Can see, sir.
Yeah, okay, thank you. Right now, to get the whole infinitely long current carrying conductor, the theta should be vary. Anybody can say theta should be vary from yes, theta should vary from minus infinity to plus infinity. When it is actually representing minus infinity to plus infinity, then it will represent the whole infinitely long current carrying conductor, right? Infinitely long current carrying straight wire, right? That way. So the same thing, that means I have to integrate this one from minus infinity to plus infinity, right? To get the whole magnetic field, right? But I can separate from middle point of the, that means I can separate from this point, this area and this area. Those are actually that is same. So therefore, I will rewrite this one, right? I will rewrite this one. I consider as this one, this is as a theta angle, right? When I am taking this the theta, right? It will come to this point, right? Then the theta is equal to 90. Right? Theta. No, theta is equal to 0, right? From 0 no, I will separate this one from this point to the infinity, plus infinity. That I will separate this one. So then from here and from here minus 1. Both are actually that is symmetric one. So therefore, I will separate into this one, right? By the earlier case, it's actually we have to integrate from minus infinity to plus infinity, right? So now I will separate from this point, actually I will consider as a 0 one, right? So twice of the 2 times of 0 to infinity dB, 2 times of 0 to infinity, right? 2 times of 0 to infinity. ds the small segment, right? ds that small segment, right? ds this small segment, because this is the function actually we are using ds, right? ds should be minus infinity to plus infinity. So therefore, I will separate from this 0 point to the plus infinity. That is twice, because it is something symmetrical line. So therefore, twice of this one from 0 to plus infinity. I can take it as you can see that 2 is there, right? Then now it will be easy now. Right. Now in the presentation, you can see now we have to here it is from this point we have to integrate from 0 to infinity 2 times of the one. The otherwise, in the previous case, minus infinity to plus infinity. Now dB, we know the dB is this one. So there actually we can substitute dB due to the small ds segment. We will write it like this one. Then the r squared is equal to s squared plus r squared. right? Sine phi minus theta, that is, we can write it as sine theta is equal to, that is sine phi minus theta, that is equal to r divided by a squared plus the square root of this. Then substitute, we can substitute the sine theta 1. Then finally, we will have like this. So therefore, now we have to integrate this, right? So when you are integrating this one 0 to infinity, we will get this. All right, we will get this. So therefore, now you can see in the previous that when you are studying at the A level, the just it is some mathematical part is actually involved in there. That's why for the A level it is not introduced. Now you may have learned about this mathematical part and other thing. So therefore, now we can you can work out how to derive the magnetic field due to long, infinitely long straight wire from r distance, right? So that is okay. So the next one, magnetic field. Magnetic field at a point on the axis of the circular coil, right? Right? On the axis of the circular coil, right? You know that magnetic field due to central. If we have a circular coil, we know the magnetic field due to center. What is it? Anybody can say? Magnetic field due to the circular coil having radius r, capital R. What is the magnetic field at the center? Mu naught I divided by 2r. Mu naught I divided by 2r, right? But here, magnetic field at a point on the axis of a circular coil, right? From x distance or z distance from the center. Same thing actually we have to apply. Same thing actually we have to apply. So there actually the only problem is actually the selection one. The way of selecting the ds, right? The small segment. Small element and the current and the distances, right? Now you can see that one. Here we have the circular coil, which is having radius r. There we are selecting the dl, the small segment or small element, dl, small element. So therefore that we can apply the due to this dB, right? Magnetic field. That is equal to mu naught divided by 4 pi I delta L r square. I delta L r square. Why? Because these the sine theta part is actually not prime because of the perpendicular. Sine 90 is equal to 1. Right? Straight away that we have written that the I delta L, then sine theta part, that is sine theta that is equal to 90. When you are taking the center, right? So now if you are taking this z distance on the axis, right? There we have to select this, right? Now due to this the small segment, right? Due to this small segment, that is the one actually you have draw it. So magnetic field is actually in this direction. Perpendicular direction. That is the dB. This one. But we want to know that the we have taken that the component along the axis and perpendicular to the axis, right? So what will happen here? There's a one part of this one, right? If I separate this into one part, this part actually we will have along the axis, that is okay. There's no change. But the perpendicular to the axis, actually, that is because of this part in one direction. But due to this other part, the magnetic field is actually that is in the other direction. Right? So therefore, this dBx is actually that is cancelled out. That is cancelled out. So therefore, only a distance that is equal to dz, that is along the axis. The other part, the perpendicular part, will cancel out due to the when you are considering about the whole circular loop, right? Considering about the whole circular loop, the other part is actually that is cancelled out, right? So in that case, we can write down some sine theta. That is, this is the expression for the sine theta, r divided by r z plus r squared. So therefore, that is there. So after substituting this, it will be equal to this one. So then dz actually that representing this, right? Now what we have to do, we have to integrate this. We have to integrate dl from 0 to 25r, right? 25r. But if we want to know about this the center, we should introduce z as a 0. Z as 0, because that is equal to 0, because that is at the center. So and at the center means z we can substitute as a 0. Okay. Then at the center, that is equal to mu naught I divided by 2r. Mu naught I divided by 2r. Suppose if we have n number of coils, so we have to multiply by n. Right? We have n turns, we have to multiply by n. Now the third application is actually we can consider as a solenoid. Right? We can consider as a solenoid. So solenoid is actually, that is B is equal to mu naught Ni. B is equal to mu naught Ni. So we have the solenoid here. There actually we have number of turns actually, that is n. The number of turns n means in the unit length. Number of n means actually that is the unit length. Suppose if we have a capital N number of turns, then with the L distance, then we have to consider about the capital N divided by L. Capital N divided by L. So that number of turns in the unit length. So therefore, here n is equal to the number of turns in the unit length. So those are the actually the application of the Biot-Savart, right? The three application of the Biot-Savart law. Ampere's law. And there is another way of actually representing the Ampere's law. Ampere's law says there we must have the line integral, right? The line integral of the magnetic field. Line integral of the magnetic field be around any closed path, right? Line integral. So therefore, magnetic field must be a line integral. It should be a closed one, right? any closed path is equal to the permeability times the current flowing through the currents flow through the area enclosed by the path. Right? Right. So by using the Ampere's law, we can easily derive the magnetic field due to the long current carrying conductor, right? So we have used a different method, but by using the Ampere's law, right? By using the Ampere's law, we can easily derive this equation. Right? The Ampere law says there should be a circular magnetic field. It should be a closed one, something like this one. Then if there's a current passing through there, current carrying conductor. These are actually currents. This is actually magnetic field. I1, I2, I3. Right? I1, I2, I3. Right? So then the total current is equal to I is equal to I1, I2, I3. Right? So this is actually magnetic field. This is a magnetic field. Right? So the Ampere law says the B, magnetic field, B dot dl, the circular, is equal to mu naught I. Mu naught I. The total summation of the currents. Summation of the all these currents. Right? And this is actually the Ampere's law. So similarly, we have derived this for the Coulomb's law also. Right? For the Coulomb's law also. Right? Actually, that is similar. Now I will derive this magnetic field due to the suppose if we have current carrying conductor like this one, then the current carrying conductor due to this is a circular one, right? Like this, right? So therefore, the radius of that one is R, right? That is R. So now the current is passing through the conductor, that is equal to I, right? Here I can write down V dot dl. dl is equal to mu naught I, right? V, the magnetic field that is due to this current carrying conductor V, dl is equal to 2 phi r, right? 2 phi r. The total distance of the magnetic field, circular path, right? 2 phi r is equal to mu naught I. So therefore, V is equal to mu naught I divided by 2 phi r. The dl is equal to the whole path of the magnetic field, right? Magnetic flux line. So therefore, dl is equal to the circumference of the field line, right? So that is equal to 2 phi r. So therefore, in that case, we can derive this B, magnetic field is longer mu naught I divided by 2 phi r, right? That is by using the Ampere's law, the application of the Ampere's law. Now, there we are going to talk about this force. Force on a moving charge due to the force on the moving charge in a magnetic field, right? So before that, we should learn about this Fleming's left-hand rule and the right-hand rule, right? Fleming's left-hand rule and the right-hand rule. So this one actually we can call it as the right-hand screws law or Fleming's left-hand, right? Right-hand screws law. All right, right-hand screws law means you can see this because they are now here it will represent in the three vectors, right? The current, the direction of that the current and the magnetic field, and due to this one actually that we have a force, right? So then the B and I should be there. B and I should be there. So therefore, when we are combining that, right? When you are rotating that, when you are rotating, we are taking B cross I like this, right? B cross I. Then you know that the cross product representing this. Okay, give me a minute, right? Two variables, the B and I, but the final one is the force, right? Two variables are actually changing, but it will represent the final one is actually that will represent the direction. So something like that. Right? The rotate the right hand screw from direction of I towards B. The direction of advancement of the screw will be the direction of the F, right? But this is a familiar for you, right? This is the familiar one, that is Fleming's left-hand rule, right? The Fleming's left-hand rule. So the left-hand rule means the B and I, the perpendicular to each other. The thumb actually, that is when you are keeping the first finger and the second middle finger perpendicular to each other. Then the thumb is also that after keeping that one for the perpendicular, the B and I actually that is representing the current and the perpendicular direction. Thumb is actually that is in the perpendicular direction, that will represent the force, right? That will actually represent the force. Yes. Force on the force on moving charge in the magnetic field, right? So then here actually we are representing in the vector notation, right? In the vector notation. So therefore, we have the charge which is moving, entering with the v velocity to the magnetic field. Magnetic field is actually that is into the paper, right? You can see the magnetic field is actually into the paper, right? That's why we can see as a cross. So then the force actually that is representing as the Q V cross B, V cross B, V cross B. So the perpendicular direction, the V and B are actually perpendicular to each other. So the perpendicular direction of that V and B actually represent the force. Right now you can see we are using the left hand. The B is actually into the paper. That the B is actually into the paper. Then the charge is actually moving that direction. So perpendicular direction actually that is representing the force, right? It will represent the force. Right now, in other way of actually that suppose the charge is actually moving through the both magnetic field and the electric field, right? Both magnetic field and the electric field, then the Lorentz force that both it will affect the electric field also. So there's a force due to the electric field also, and the force due to the magnetic field also, right? Force due to the magnetic field. Now, the current means the flow of charges. The current means actually flow of charges, right? The magnetic force on the current carrying conductor, right? Magnetic force on the current carrying conductor, right? So the current carrying conductor means the flow of charges. The flow of charges. Suppose that if you have a current carrying conductor, in the magnetic field, right? In the magnetic field, so then there is a force on the current carrying conductor because all these charges which is moving along the current carrying conductor. So therefore, suddenly there is a force perpendicular to both the direction of the current and the magnetic field, right? Direction of the current and the magnetic field, right? Direction of the current and the magnetic field, right? Now you can see that right now actually you can see the magnetic field. Suppose we have shown that part of the current carrying conductor magnetic field is actually into the display. It will represent as a cross. So therefore the current is actually into the magnetic field is actually into the screen. So the charges actually moving to the left hand side, right hand side like this. Then you can see that the force due to the charges, it will move up, right? The force is actually that is in the upward direction, right? So that the equation for the force is equal to F is equal to I delta L into B. I delta L into B. I delta L into B. Right? I delta L into B. So the finally when you are taking this the perpendicular direction, that is equal to the force is equal to BIL. BIL. Then you can see we have a right. Now you can see that there are some pictures. The I is equal to I is equal to 0 that way. So when the I is actually that is upward direction, the one direction. I is actually that is downward direction. The force is actually that is in the other direction. Right? Force is that is in the other direction. Now this is actually very interesting. And now there's definitely there should be a magnetic field to have the force. Even that current carrying conductor or the charge in the magnetic field, there should be a magnetic field, right? But we know that if we have a current carrying conductor, then due to the current carrying conductor, there's a magnetic field generated there, right? Infinitely long current carrying conductor, that is, there's a magnetic field. So we know that that is equal to mu naught divided by 2 pi r, right? Suppose if we have two parallel, right? Two parallel current carrying conductors, right? Then the one is actually that is you can see due to current I1, there is a magnetic field on the I2, the second current carrying conductor. So the magnetic field is equal to mu naught I1. The separation between that is equal to R. So mu naught I1 divided by 2 pi R. But now it is perpendicular to the current carrying conductor, right? Perpendicular to the current carrying conductor. So therefore, but in the second current carrying conductor, the current is equal to I2. Now there is a current carrying conductor, and the conductor is also there, and the magnetic field is also there perpendicular to the current carrying conductor. Then there is a force. Right? The force is equal to I into delta L B, but B is equal to the B actually due to the conductor 1. B is magnetic field actually due to the conductor 1. So therefore, finally we can write down F I2 L B. B is equal to mu naught I1 divided by 2 pi r, right? So the force per unit length, actually, finally we can represent as force per unit length is equal to mu naught I1 I2 divided by 2 pi r, right? Mu naught divided. So this is one application of the both the Biot-Savart law and the Fermi's left hand rule, right? Any application of this one? Can you explain? Anything? Have you seen this one? That any applications? Yes. Two parallel current carrying conductors.
Seen, sir.
Sorry?
Have not seen, sir.
Okay. Have you seen this? What is this? The ampere balance. You may have done during the experiment. This is totally based on the two parallel conductors, two parallel current carrying conductors, right? Two parallel current carrying conductors. So by using the Ampere's law, we can find this mu naught, right? We can find the mu naught. So, and this is also involving to define the ampere, right? The unit of the ampere, right? So then when we are keeping this is the definition of the 1 ampere. Suppose if we are having two parallel conductors and separated by 1 meter, the both the currents are same, right? So then I can write down F is equal to mu naught I divided by 4/5 into I squared by 1. Actually, what is the value of mu naught? Mu naught is equal to 4/5 into 10 to the power minus 7. Mu naught is equal to mu 2/5. No. This is 2/5. 2/5 R. It is the force is equal to F is equal to the force between that. Force is equal to mu naught I both the current side, that is equal to I squared, right? Both I is equal to then 2/5 R. 2/5 R, right? Now I can substitute. Mu naught is equal to 4/5 into 10 to the power minus 7. I will keep it as I squared. Then divide by 2/5 into R is equal to the separation between the two conducting wires, that is equal to 1 meter, right? So this is actually that is 2 I squared. So the force is equal to 2 into 10 to the power minus 7 into I squared. Okay. Suppose I is equal to 1. When the 1 ampere is actually passing through there. When the 1 ampere is actually passing through there, right? 1 ampere is actually passing through there, then I squared that is equal to 1. So finally F is equal to 2 into 10 to the power minus 7. Okay. I is equal to 2 into 10 to the power minus 7. Right? Right? Then this is the final equation we can write down. F is equal to 2 into 10 to the power minus 7 I square. Right? If I is equal to 1, then the 1 ampere is actually passing through these conductors. The force is exactly equal to the 2 into 10 to the power minus 7. Right? So definition of the 1 ampere means if the force is equal to 2 into 10 to the power minus 7. If the force is equal to 2 into 10 to the power minus 7, then actually we can say there is a 1 ampere is actually passing through there. It is happening when the 1 ampere is actually passing through each of these parallel conductors, right? Each of the parallel conductors, right? Right. Now we are going to talk about this torque on the current carrying on the rectangular coil. Right. Now we have a rectangular coil. Then there is a torque on the rectangular coil. Right. Now the rectangular coil means now we are actually coming to the slowly we are coming to the what? This is moving coil galvanometer, right? Moving coil galvanometer. So then after coming this one, then I will explain this torque, right? This is actually related to the application of the galvanometer and the motors. Right. Here you may have already done the application of two parallel conductors, that is ampere balance, right? So by using this ampere balance, we are deriving this mu naught, right? We identify this mu naught. What is the value of the mu naught? Right. Now, so far actually we are talking about this magnetic properties of some materials, right? There are three categories, right? There are three categories of magnetic properties. What are those things? Anybody? Somebody has went through this lesson material? Nobody.
Diamagnetic,
Magnetic.
paramagnetic, and
Yes.
ferromagnetic.
Ferromagnetic. Anybody can explain that? What do you mean by this diamagnetic? Yes. What is this diamagnetic, paramagnetic, and ferromagnetic? Yes. Yes. You understand that what is this diamagnetic, paramagnetic, and ferromagnetic?
Lines of
Yes.
force, do not like to pass through the specimens.
Yes.
Those materials known as diamagnetic.
You're talking about diamagnetics.
Yes, sir.
So in the book it says this is caused by a motion of electrons around the atomic nuclei.
This is actually due to that the atomic structure of the material. That is correct. That is also correct. Right? How we are going to identify this, whether this is a diamagnetic material and a paramagnetic material?
Consider about attraction and repulsion of poles of the metals.
Yes, yes, good, good. Okay. You may have some idea, but you have to, what you have did, you have to put them in the align, right? Okay, then I will just show you the small video related to that one, right? උඩ තිබිලා. ආයතන උඩ තිබිලා.
You might not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass.
I mentioned
This
about
is a
few
new and different
parameters,
category of
right?
magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized
You can see that the paramagnetism, right? It is something like iron. Yes, what
piece
will
of
happen?
iron or nickel or cobalt becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet.
Aluminium is a
And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed.
see the diamagnetism is a totally opposite of the paramagnetic material, right? It is always opposite repels.
They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present when they're chilled. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields. One way to check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field.
So now you
Diamagnetic
can
objects
see
like-
that the what will happen that diamagnetic magnetic material when it is aligned with the magnets.
Glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic field. But aluminum rotates into the field, typical of a parallel paramagnet. On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p. Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet like water? Yes, the water molecule. It has all of its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons come to
So
lower
that means
energy
water
as
is
they are moved away from the magnet.
Diamagnet. It is that will
In
repel.
conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are doing. In the case of a paramagnet, it has at least one unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
Okay, then you may learn few things about this Yes, diamagnetic, right? When subtended in a uniform magnetic field, they set their longest axis to the right angle, to the magnetic field as shown, right? Because it is a weaker magnet, right? The line of force does not prepare to pass through the specimen. Line of force, that means field line is actually not passing through the specimen, right? Since the abilities of a material is permits the passage of magnetic lines of force through, it is less. Diamagnetic specimen, the closest to the magnet, behave like a smaller pole of magnet, and thus it repels. These are the examples of diamagnets: bismuth, antimony, copper, gold, quartz, mercury, water, that is alcohol, air, and hydrogen. And paramagnetic. The paramagnetic substances develop a weaker magnetization in the direction of the magnetic field. It will also align with the magnet. And the paramagnetic rod is actually subtended freely in a uniform magnetic field, that is also in the direction of the magnet. It's aligned itself in the direction of the magnetic field. The line of force prefer to pass through the magnetic material, right? The closest side of the paramagnetic specimen behave like a pole of magnet, and it thus attracted. So the examples actually aluminium, platinum, chromium, manganese, copper, copper sulfate, and oxygen. Those are paramagnetic material. Then the ferromagnetic. These substances are get strongly magnetized in the direction of the field. The line of force prefer to pass through the material, right? And especially that the examples iron, cobalt, nickel, number of alloy material, right? All substances, including liquid, gas, fall into one of these categories, right? These are the behavior of this. So now we'll see that the infrastructure of this simple magnetism theory of magnetism, right? So the total magnetic moment, actually that this is happening. We are talking about the atom, right? Nucleus that is at the center. The electrons are actually orbiting, right? Spinning around the nucleus, and meantime it is spinning also. It will rotate self in that axis, that is called spinning, and while it is rotating around the nucleus, so therefore spinning, there is a magnetic movement, right? Spin magnetic moment is also there. When it is orbiting, the magnetic moment is also there, right? So that the spinning electron means spinning magnetic moment, and when it is orbiting, while it is rotating around the nucleus, then orbiting magnetic is also there, right? But the problem is actually the total magnetic moment, that is due to the spinning magnetic, that is in the other direction. The orbiting of the electron, it is somewhat strong. So therefore, we will have the final one, the total magnetic moment. When the matter is actually subjected to external magnetic field, there are two bases of effect. The electron motion is actually distorted, and any permanent magnetic pole becomes partially oriented, right? So therefore, the matter is actually subjected to an external magnetic field. That there are two things actually that is happening. That electron motion is actually that is distorted due to the external magnetic field. So the classification of magnetic material, diamagnetic, right, induce resultant dipole moment. So therefore, this is caused by the motion of electron around the atomic nucleus. So all electrons are actually paired electrons, as we have mentioned about. We have already shown that one. The water molecules all are actually paired one. So therefore, there is no resultant magnetic dipoles. You have seen that one in the video. So it is a very weak effect of the effect, and the independent. It is independent of the temperature, right? It is called diamagnetic material, diamagnetism, right? Diamagnetic material when you are placing in the magnet. The paramagnetism have some molecules or atom in which there are some unpaired electrons. We have seen that one aluminium. There's an unpaired electron. Hence, they exhibit a magnetic dipole movement, right? So therefore, the paramagnetism is actually strong at low temperature. Ferromagnetism. It is a characteristic of ferromagnetism. Can be explained by the presence of domains, and paramagnetic domains is a small region of matter which is contain atoms and the molecules. Magnetic movements are aligned in the same direction, right? Individual paramagnetic atoms are paramagnetic and have their unpaired electrons, right? So the direction of magnetization in different domains are not necessarily parallel to one another. When the specimen is actually placed in the magnetic field, the resultant magnetization many increases in the two ways. Right, in the surface current, right? Now, when you are moving to the surface current, right? The total surface current, that is IS, around the periphery of the portion of the cylindrical of length I is given by IS is equal to M into L, right? M is called the magnetic property. And we have two types of currents. One is called the conduction current. The other one actually we can call the surface current, right? So now you can see that the surface current. Here we have drawn the surface current, right? And capital I is called the conduction current. Magnetic field strength. By using the Ampere's law, the as we have mentioned about this, the mu naught IL, right? The B is actually that is due to the surface current, that the B is actually due to the total current, and the IS that is due to the surface current, right? So therefore we can write down these by using the Ampere's law. We can write down that the one expression for the surface current, then the other one actually that is called the total current, right? So then the magnetic field strength we will define as this, right? So the finally we can write down the B as a subject, right? B as a subject actually, B is equal to mu naught H into M. Then we have the susceptibility, right? Magnetic susceptibility of the material is defined as the magnetism per unit magnetic intensity, right? Magnetization per unit magnetic intensity, right? So therefore that the susceptibility Xi is equal to 0 for vacuum. Psi is actually that is greater than 0, that is for paramagnetic material. Psi is actually that is less than 0, that is a negative value for diamagnetic material, right? Diamagnetic material. So therefore that we can write down with similar actually the expression actually we have found in the electric field also, right? Here it is the epsilon, the relationship between the epsilon and the that electric susceptibility. Here we are talking about the magnetic susceptibility, right? So therefore that permeability, relative permeability is equal to the 1 plus magnetic susceptibility, right? Magnetic susceptibility. Suppose if the relative permittivity is actually that is less than 1, the material actually we can categorize as a diamagnetic one. If the relative permittivity is actually greater than 1, the magnetic material is actually that we can categorize as a paramagnetic material, right? So therefore, finally, that we may have already done that the experiment related to this hysteresis curve. So therefore, that the hysteresis means that is related to the external field and the magnetic field due to the current, right? Magnetic field due to the current, right? So therefore, that when you are conducting this experiment, you will get this kind of the graph, right? From the graphs, actually, you have found that you have found the constant, right? So that is actually that you know that I have already explained this why we are doing this one, right? So then we have learned about this the magnetic material, right? Then finally that application part is there. Finally, that we have the application part, right? So the application part means it has actually finally converted to the experiment, right? So now we have learned something, the materials, right? Magnetic materials. So therefore that now we have categorized in this how the behavior of the magnetic materials, right? Whether it is a paramagnetic, so how it is looks like a hysteresis curve. For the paramagnetic, what will be the shape of the material, right? So you can see that one, it is totally depending on the energy loss, right? The shape is actually that is representing the hysteresis curve, right? Right. So then now from this point onwards, we will discuss next day, that is our next day school, that is on 17th, I think, Yes, 17th. The coming Monday around 10:30, right? So after that one, we will, after that, actually, we will discuss about maybe 1 or 2 day schools, right? So you better tell me what is the possible time for you, because that assigned day school, actually, we have only 2 before the CAT exam, right? Before the CAT exam. So you better tell me, I can assign that 2 or 3 days. I don't know whether it is possible for you. Any idea? Any comments?
So this 17th holiday, na?
Yeah, that is a holiday, but that master timetable, that is a POE day. That is a POE day, but they have assigned that the day school from 10:30 to 12:30.
It's okay, sir.
Right? Okay, right. We'll see whether the time permits. We'll go up to 1 o'clock or 2 o'clock, something like that one. The other than that, I mean, talking to that, because there's, the screen also, that is maybe 2-3 hours. It is a very boring thing, and listening to that one also, it is a very boring thing, right? That's why that we have categorized in 2 hour sessions, right? Because maybe some of the students, actually, that is morning time also, that you have participated in this practical session also. Right. Anyway, how about this? The after 17, that means before the CAT exam. You know that CAT exam, that is on February 5th, right? February 5th.
So it's based on
Unit 2.
sir, unit 2, all unit, na, sir?
All unit. Yes, all unit.
It's just like MCQ was
No.
It
It is an on-site one.
Yes.
You have to come to the regional center,
Okay.
right? You have to come to the regional center, then
It's just like not MCQ.
not MCQ actually. Not, there will be 2 questions. You should answer to all the questions, right? It is essay type one, structure, essay type one, not the structured one, essay type one.
Sir, this is a small request.
Yeah.
Sir, can you send some second NBT past papers to learn always? We couldn't get
Is there any, I think there will be some papers in the Learn Now essay.
NBT. I didn't see, sir.
You didn't see?
Yes, sir.
I will check that one. I will check that one. Otherwise, if there is no MBT, I'll put 1 or 2 NBTs. It is totally based on this the unit 2, and maybe not the last part, right? The transition of is maybe magnetic field, the Biot-Savart law, Fleming's the left-hand rule, right-hand rule, right? And the magnetic materials, right? Maybe first and Biot-Savart, the Fleming's left-hand means we have 2 parallel conductors. That one. The paramagnetic one. Ampere's law.
Not coming about transformers, sir.
Sorry?
Transformers.
Yeah, I should say that is one, two, three, 4. Four, 5. Up to 13, including 13 also. We didn't have enough time to read these things. Right? From lesson numbers up to, I will place it from 9, starting from 9 to 13, including 13. Not this induction one. Right? Before that. How many lessons? 1, 2, 3, 4, 5. 4, 5. Right? 5 lessons are there for the CAT.
Okay, sir.
Just 2 questions, 1 hour paper, 2 questions. You should answer all the questions. Maybe very, very simple one. Not a very hard one. You can go through these self-assessment questions and other thing. According to that one, we will see.